The last set of notes in this unit deals with the ideal gas law equation. The ideal gas law equation is sometimes referred to, actually it's quite often referred to as the pervert equation. For whatever reason, chemistry teachers across the country refer to it that way. It looks more like Pubnert, but this pervert equation deals with the relationship between pressure, volume, temperature, and moles of a gas again. But it doesn't talk about changes in those variables. It's just about one specific set of conditions. And this is what I call an R-driven equation. An R-driven equation is one that has this ideal gas law constant as part of the equation. And here's the important part. It's the units. Liter atmospheres per mole Kelvin. Now, we usually call them Latam molts, liter atmospheres per mole Kelvin, again as Latam molts. It's just a little bit easier way to keep it in our heads for what those units are, because all of our other variables must be in those units. Volume must be in liters, pressure must be in atmospheres, we have to have moles of the substance involved, and temperature, as usual, has to be in kelvins. When we were dealing with the combined gas law, it didn't matter what units we dealt with pressure and volume in, just the temperature. But now it does matter. It has to be in these units, and if it's not in these units, we're going to have to convert to these units. Now we can also write the equation, as we've done before, as mass over molar mass in place of moles times R and T. Now, a lot of people like to see it like this because it helps them remember where that molar mass value is. So molar mass is on the bottom, M, R, and T are on the top. And so the mass over molar mass is a substitution for the number of moles. Just depends on whether the problem deals with moles or whether it asks you about grams or mass. So let's look at this example. It says a steel cylinder at room temperature, 27 degrees Celsius, with a volume of 25,000 milliliters, is filled with nitrogen gas to a final pressure of 150.000 millimeters of mercury. What mass of gas does the cylinder contain? So it's asking us to find mass. So we know we're going to be using the M over M, the mass over molar mass form of the equation. So let's go ahead and write that out. QB equals mass over molar mass times R times T. So we'll write it like this. It's a little bit easier to solve for. We're looking for mass once again. And so to solve for this, we're going to need to multiply both sides by molar mass, which is going to reduce it to 1 over on the right. And we're going to divide both sides by R and T, which is going to, again, reduce to 1 or cancel over here. Divide by R and T over here. So we'll end up with the fact that mass is equal to the molar mass times pressure times volume over the gas law constant R and temperature. So let's plug these values in, and please remember we must pay attention to what the units are in, and for the gas law equation, for the ideal gas law equation, because it is R driven, those units have to be in Latam molts. So plugging in these values, we get that mass is equal to the molar mass, and we need the molar mass of nitrogen gas. Now be really careful. We look up nitrogen, and it would be really easy to put 14.01 grams per mole. But remember, nitrogen is diatomic in 2, so the actual molar mass is going to be 28.02 grams per mole. So be very careful with gases. You have to pay attention to what their formulas are, if they're diatomic or not. So the 28.02 grams per mole our pressure says the pressure is 150.00 millimeters of mercury, and hopefully you realize right off that that's not going to work because, again, it's R driven, Latam molts. This has to be in atmospheres, so liter atmospheres, moles, and kelvins. So let's do a little side calculation. If we've got 150 millimeters of mercury, and we know that there are 760 millimeters of mercury per atmosphere, then we're going to end up with a value of 0.1974 atmospheres. I'm not really paying attention to sig figs here. I just want to make sure that we have plenty of sig figs, at least one or two places past where we'll need to round this to at the end. And notice that we have 2 sig figs for the 27 degrees and also for the 25,000. So if we have 4 sig figs on this side calculation here, we're going to be okay. So let's put in the pressure then of 0.1974 atmospheres. And then our volume is 25,000 milliliters, which hopefully you've thought of already that won't work because milliliters has to be converted to liters. It's got to be liter, atmospheres, moles, and kelvins. So changing that to liters, rule of 3, moving the decimal place to the left 3 places, or the decimal point to the left 3 places, ends up giving us 25 liters. On the bottom then, our gas law constant is 0.0821 lattimolts, liter atmospheres per mole Kelvin. And then our temperature, since our temperature is 27 degrees Celsius, remember we have to add 273. That's always true with the gas laws. So we're going to end up with 300 kelvins. Looking at what cancels, looks like our moles cancel, liters cancel, atmospheres cancel, and kelvins cancel. And all we're left with is grams, which is a valid unit for mass. So when we put this in our calculator, remember 28.02 times 0.1974 times 25 divided by 0.0821 divided by 300, we get a mass to 2 sig figs of 5.6 grams. So there's our answer to the first problem. And one more. Now I may ask you all kinds of questions about the ideal gas law. You may be solving for mass, for volume, for pressure, for molar mass. We're not going to do examples of all of those, but you very well may find those on the worksheet, so watch for those. A variation of the ideal gas law is a density equation. Now we can derive that from the gas law, but I prefer to just memorize that the density is equal to the pressure times the molar mass over R and T. And I've always remembered it because I'm a morning person, and so when it gets later and later at night, I get a little bit denser and denser, or more dense and more dense, however you want to put it. So I am dense at night, PM, right. Dense at night, right. That's how I've always remembered this equation. So however you choose, whatever mnemonic device that you choose to remember this equation, D equals PM over RT. So as soon as it asks me for the density of a gas and it gives me values for pressure and temperature, I know I'm using this equation, D equals PM over RT. Since I'm actually solving for density, I don't need to rearrange this equation, but it's still an R-driven equation. As soon as we see that we're dealing with R, liter atmospheres per mole Kelvin, I know that this 520 millimeters of mercury is not going to work, and neither is the 125 degrees Celsius. So let's do a side calculation on the millimeters of mercury. If we've got 520 millimeters of mercury, and we know there's 760 millimeters of mercury per atmosphere, then I end up with 0.6842 atmospheres. And again, this is going to be another 2 sig fig equations, or answer, so having this be a couple of places past what I need it to be should be sufficient. So there's the value I'm going to plug in for my pressure. So density then is going to be equal to the pressure value we just found, 0.6842 atmospheres, times the molar mass. Watch it again. Oxygen is 16.00 but grams per mole, but oxygen is diatomic. So make sure you remember to check for that. These gases, they'll sneak up on you. 32.00 grams per mole. Divide that by our gas law constant, 0.0821 latomoles. And then the temperature, since the temperature is 125 degrees, if I add 273 to that, I'm going to get 398 kelvins. Canceling, looks like we've got kelvins canceling, atmospheres canceling, moles canceling, and we're left with grams per liter, which is a valid density unit for gases. When we're dealing with solids and liquids, we usually do grams per milliliter or grams per cubic centimeter. But gases have such a low density that it's much better to deal with it in terms of grams per liter. So dividing these out, 0.6842 times 32 divided by 0.0821 divided by 398 to 2 sig figs, we get, I better put density equal to 0.67 grams per liter. So that's our answer.